Dos, tres, cuatro.
Hi everyone, welcome to the final lesson of Pre-Calc 12. We're going to take a look at double angle identities, and we're going to build upon some of the things that we learned from last class. So as you can remember, we had something in which we learned sum and difference identities. An example of a sum and difference identity was sine x plus y, and we know that that expanded to create this statement right here. In order to prove our double angle identities, we're going to take a look at some algebra to be able to manipulate this a little bit. Imagine in the statement of sine x plus y that you're going to replace your y's with x's. If you did something like that, then wherever there's a y, let's write an x. So you could say here we have sine of x plus x, and then what that means over on the right side is wherever you have a y, we're going to replace it with an x. So if we do that, we would now have sine 2x, and that's going to be equal to, well, sine x cos x and cos x sine x, they are the same. So you could actually join them, and you could say that that becomes 2 sine x cos x. These are like terms. I could just rearrange the order of them right there. And based off of that, we've created something called a double angle identity. And if you take a look at your formula sheet, you'll notice that right here, that's going to be one of the identities that is going to be listed there. And we're going to use that for some of our additional questions today. Now, how would that work with cosine? Well, let's do the exact same process here with the cosine sum identity. And we can remember what that expanded to. And once again, let's replace our y's with x's. And if we do that, we could get cosine of x plus x, and it's going to equal, something that would look like this. Cos x times cos x right here becomes cos squared x, and sine x times sine x becomes sine squared x. And so cos 2x of getting this x plus x will equal cos squared x minus sine squared x. Now take a look at your identity sheet, and you would say, well, when I look at my cosine 2x identity or my cosine 2 theta identity, there's 3 different options of what that could potentially become. So we've covered one option right here by saying we have cos squared x minus sine squared x. But let's create a couple more identities right now. So let me just take a look at what we have right here. If we wanted to write a Pythagorean identity, and we know that sine squared x plus cos squared x equals 1, and we have our cosine 2x right here. Well, we could say that cosine 2x is going to equal, instead of saying cos squared x, I could substitute the Pythagorean identity and write 1 minus sine squared x, and then subtract my regular sine squared x right here. And that means that cos 2x will now be equal to 1 minus, well, these are like terms, 1 minus 2 sine squared x. So take a look at your identity sheet, and you'll see that that is a second option for what you could change cos 2x into becoming. The third option would be changing everything into cosines. And if we have cosine 2x and we look back up here and we say, well, that's equal to cosine squared x minus, well, if instead of saying sine squared x, I substitute it with the Pythagorean identity to say, to replace it with something here that says 1 minus cos squared x, and we distribute the negative, we could say cos 2x equals cos squared x minus 1 plus cos squared x. So cos 2x will be equal to 2 cos squared x minus 1. So we have 3 options for double angle identities when talking about cosine, and those are just all manipulations of each other. You'll take a look at the summary at the bottom right here, and you'll see our sine double angle identity, our cosine options for their double angle identities. We're not going to go into this in terms of details, but just understand that you could also create something using tan, and it's a very similar process to what we've done with sine and cosine. If you take a look at Michelson on page 337, you'll be able to see a quick explanation as to how they manipulate that. Okay, so what would we do to solve something like this? Now, no one's going to do this, but we want to make sure that this is super clear that if you say cosine 2x, there's no way that that's equal to 2 cos x. You can't move that 2 in and around with the cos x. And so once you know that that's not the case, whenever you do see this 2 in the middle, we know that we have a double angle identity, and then we know that we're going to be trying to do something to expand it and change its form to make it into something that we could either solve or prove. If you look on the right side, we have something only in terms of signs. And so when trying to figure out what to change cosine 2x to become, and you have your 3 options, I would change it to the option that has only signs, because the right side only has signs. And if you can work with just one trig ratio, that's going to be better than working with multiple trig ratios. So with cosine 2x, let's change that to become 1 minus 2 sine squared x equals 2 sine squared x. And then think about what they're trying to solve for. They want all solutions here between 0 and 2 pi. Let's get our sine squared x's onto the same side. So you could add 2 sine squared x onto the right side. And if you have something like this, we can now try to isolate for sine. So we could divide by 4, 1 over 4 equals sine squared x. We don't want sine squared x, we just want to solve for sine x to be able to figure out exactly where we're going towards, and then after that, it's just to solve for x itself. So to get rid of the squared, we could square root both sides, and understand that when we take its square root, we're creating a plus or minus situation because we've created a square root. So we'll have plus or minus 1 over 2 equals sine x. Based off of that, we can now say, well, where would I have solutions amongst my 4 quadrants? And because it's plus or minus, we actually have a solution in every single quadrant. And if we draw our triangles in each of the 4 quadrants, and you look at, say, for instance, the first quadrant, and you said, well, sine x equals, so opposite over hypotenuse, 1 over 2, then that's going to give us our 30, 60, 90 ratio. They're asking for our answer in radians, so we could say our reference angle in quadrant 1 is going to be pi over 6, and pi over 6 will be our first solution between 0 and 2 pi. But because it's plus or minus 1/2, we have an answer in quadrant 2, an answer in quadrant 3, and an answer in quadrant 4. And so as we list these out right here, we create other pi over 6 reference angles, and we want to figure out what are each of these individual terminal arms. And as we work that through, I know we've done these a bunch of times, you would get 5 pi over 6, 7 pi over 6, and 11 pi over 6. And these would be our 4 answers between 0 and 2 pi. Now, a common question is to ask you to simplify some double angle identities. So something like 12 sine 4x cosine 4x. How could that be cleaned up in some way? And this is one of the trickier concepts to be able to work with. What you want to do is you want to compare this to a form that it looks familiar to. So hopefully if you see the question that we have right here, you would say, well, this resembles something in which I know I had 2 sine theta cos theta equals sine 2 theta. Looking at your identity sheet, this was your sine double angle identity, and the format looks really, really similar. Well, how do they differ from each other? I would say that they differ in two ways. The first thing is this. We have a 2 here, we have a 12 here. In other words, the top part here is 6 times more than what we had on the bottom. And so because of that, if you're comparing the top and the bottom, we would have to put a 6 up here to say you have 6 times more than what we had for the right side of sine 2 theta. The next thing that I would say is this. I used to have thetas, but now I have 4 x's. So wherever I have a theta, right here on this right side, I should change to or substitute with a 4x. So I get 6 sine 2 4x, and those can be cleaned up to say 6 sine 8x, and that would be my best answer on how to simplify a double angle identity. It's a strange process. If I was to say what it is, it's basically trying to create some sort of matching game for what we have. Let's take a look at the next example, and let's see what we could do with this one right here. So if you have 8 cosine squared 6x minus 4, we would quickly say, well, that pairs up with 2 cosine squared x minus 1. And if we want to do something like that, we know that that is the double angle identity for cosine 2 x. If I wanted to say, actually, maybe to be consistent with our last example, I'll use theta. Okay. And we want to say, what would that be equivalent to? So once again, take a look at what we have on the top here, and I would say that the numerator is 4 times, or not the numerator, the top is 4 times bigger than our example on the bottom. I have 8 of this object and 4 of this object. I could even factor out a 4 to show that, and if I did factor out a 4, I'd be left with 2 cosine squared 6x minus 1. So my numerator is going to be 4 times more, why do I keep saying numerator here? My top is 4 times more than what I have on the bottom. And then what we'll say is our theta has clearly been replaced with a 6x. And so if you write 4 cosine 2, I'm not going to write theta, but I'm going to write what it's been replaced with. It's been replaced with a 6x. And then we could tidy that up and say that would be equivalent to saying 4 cosine 12x. Okay, not the most straightforward. If you're feeling really good about this, then I would pause the video and I would take a look to see if you could try C and D on your own. And if it's something in which you want a couple more examples, then just keep playing. Part C now might be a little bit confusing because when we look at this, I would say it may come across as being backwards. In fact, let's do a little bit of algebra to try and manipulate this and make it look better. If we rearrange it and we said this was negative 6 cos squared 8x plus 3, and we factor out a negative 3, then we'd be left with 2 cos squared 8x minus 1. And now that form right here will definitely resemble our 2 cos squared theta minus 1 form that we're more familiar with. And we want to pair that up with our cos 2 theta. And when we look to pair that up, let's see how they match up. Well, the top part here, I won't say numerator because it's not a numerator, is being multiplied by a negative 3. Because it was backwards, we recognized that and we factored out a negative 3 to be able to rearrange it so that it could pair up more clean. And we can now say we have negative 3 cosine 2, and our theta has been replaced with an 8x. And so now we could tidy that up and say it would be negative 3 cosine 16x. Okay, and then finally, let's take a look at this last example right here. So we haven't looked at the tan identity too much, but I'll just write this out just so it's really clear. So if we have our tan identity is 2 tan theta over 1 minus tan squared theta, and that equals tan 2 theta. So when looking at a question like this, you could say, well, what's the difference between the example that we have and what we're looking at right here? Well, it looks like the top is being doubled. I have 4 tan 3x's versus just 2 tan thetas. And so we need to put a 2 in front here. And then wherever there's a theta, it's been replaced with a 3x. So 2 tan 2 3x. And then we can tidy that up and say we have 2 tan 6x. Definitely a little bit of an awkward process. I feel like this is one of those sorts of questions in which someone in class would put up their hand and say, when are we ever going to need this in life, or when are we going to use this? I'm not sure in terms of real life applications where this comes into, but I know in terms of understanding the algebra around it, it'll help you for some of your calculus problems next year. Okay, let's take a look at what we have for this next example. And so now we're back to doing proofs, but we're doing proofs with double angle identities. And this one here actually is a fairly complicated one. If you see sine 6x, just recall what you could expand that with, knowing that if sine 2 theta is equal to 2 sine theta cos theta, that's on your identity sheet right there. Could we expand sine 6x and rewrite that in some form? So let's see what we would have. If I did the same thing as what we've done for our previous questions, then I would say, well, this looks basically the same, except wherever there's a theta, you're timesing it by 3x's. And so it would create something that would say 2 sine 3x cos 3x. So let's do that right here. 2 sine 3x cosine 3x over, and then we want to know what we want to replace it with on the bottom. And this is a big point. We have 1 plus cosine 6x. And if you have something like that, the fact that it's 1 plus something means that of your 3 options for cosine double angle identities, you're going to want to replace it with something in which you are subtracting 1 to balance out the plus 1. So you're going to want to have something that has a subtract 1, meaning the 2 cos squared theta minus 1 identity, so that you'll be able to eliminate those 1s when you simplify terms with each other. Okay, so what does that mean? Well, I'll do this slowly on the right here again. So if we had, let's see, if we have cosine of 6x, and we want to know what that's going to become, and we're comparing that with our cosine identity, and we know that our cosine identity is going to be something that's going to be in the form of, well, cosine 2 theta, and it's going to be equal to 2 cosine squared theta minus 1. Will they look exactly the same? But we would once again say that instead of having a theta, we have a 3x, and we could replace it with that. So if we do something like this, and we now substitute in here, here's the original 1 that's going right there, plus bracket 2 cosine squared 3x minus 1. Well, we can now simplify that. The 1s will end up canceling each other out, and we'd be left with something that would say 2 sine 3x cosine 3x over 2 cosine squared 3x. Well, we know that the 2's here could reduce with each other. We have a monomial divided by a monomial. And the cosine squared 3x, one of those could reduce with that cosine 3x, meaning we'd be left with just sine 3x over cosine 3x. And we know that sine over cosine is equal to tan. So in this case, if you have sine 3x over cosine of 3x, that could be replaced with tan 3x and tan 3x. And they're balanced, and we've done that correctly. So definitely probably one of the harder identities that you'll have to go through. Hopefully that makes sense. There's a lot of good identity questions that Michelson has to practice with. Okay, and finally, example 4, your final example for pre-calc 12. Sine x equals negative 12 over 13 and is in quadrant 3. Find tan 2x. In quadrant in quadrant 3, let's draw a triangle, and we know that right here, opposite is going to be 12 and hypotenuse is going to be 13. So you would have to do Pythagoras to be able to find out your third side, or you could recognize that it's one of our Pythagorean triplets where that's going to be a 5, and we have a 5, 12, 13 triangle. And they're saying, based off of this, can you find out what would be tan 2x? So think about your identity for tan 2x, and we know that that expands to equal 2 tan x over 1 minus tan squared x. Well, let's see what tan x is equal to. It's equal to opposite over adjacent, which would be positive 12 over 5. The two negatives cancel each other out. So then based off of that, we can now say if we know that tan x is equal to 12 over 5, we could replace each of those tan x's with a 12 over 5. And we could get something that would say 2 12 over 5 over 1 minus 12 over 5 squared. And that's not the nicest looking fraction, so let's see what we could do to clean that up a little bit. We could get 24 over 5 over 1 minus 144 over 25. And let's continue to tidy that up. So instead of having 1, let's write this as 25 over 25. We would get 24 over 5 all over negative, what would that be? I think that'd be negative 119 over 25. And then we can times by the reciprocals, and we could say 24 over 5 times by 25 over negative 119. The 5 and the 25 can reduce, and we'd be left with 120 over 119 negative, and that would be our simplified solution for something like that. Probably not the easiest question, but definitely something in which you could simplify it down to equal something like that. Okay, Michelson, he comes out pretty hot and heavy off the bat. Some of the questions from number 1 I think you're going to find quite challenging. So here's your homework, and good luck with it, and I'll be able to help when you get a chance to go through this video. Thanks. Bye.